Welcome to Code with Vinay. In this video, I'll be introducing a problem-solving technique called recursion. I'll start from the very basics and then I'll build up from there. Do avoid the temptation to skip forward even if you find the build-up rather too gentle. The relevant extract of the syllabus from the recursion section is on your screen. You are supposed to know the concept of recursion and you must be able to apply the recursive technique to solve problems, some of which are enumerated in the syllabus itself, like factorial, GCD, binary search, and conversion from one base to another. In this video, I'll be covering all the problems mentioned in the syllabus, and then there will be follow-up videos where I'll be solving other recursion-based problems. In a dictionary, recursion is defined as the process of repeating a function, each time applying it to the result of the previous stage. So, if I draw a rectangle, rotate it by a certain angle, enlarge it, and then again repeat the process, I'm performing recursion. Let us see this in action. What is happening is, we are drawing a rectangle, rotating it, enlarging it, and then again repeating the process, which is leading to this interesting pattern. It may sound ironic, but to understand recursion, one must first understand recursion. Google, the search engine, explains this in a very subtle manner. Let us see how. So, if I search for recursion on Google, even after typing the correct spelling, it says, "Did you mean recursion?" Normally, "did you mean" is shown in case of a misspelled term, but in this case, it's Google's way of teaching us recursion. If I click on recursion, it takes me to the same page with the "did you mean" recursion still visible. See. The idea is that after clicking it a few times, the user will realize that this is recursion. That is, recursion is doing something in terms of itself. In terms of computer programming, it implies calling a method from within the same method. The recursion must end at some point when a certain condition is met. Let us see recursion in action, and we'll start with a very simple example. It is going to be a toyish example as it won't be doing anything useful, but nevertheless it is useful from the understanding perspective. So here we have our main method, and from the main method we are calling a method simple, and as you can see, the simple method has only one line, and that is it is invoking the method simple itself. And this is the recursion. We are calling a method from within the same method. On the first thought, it would appear that this would result in infinite calls. Even the ISC syllabus mentions that the computation can go into an infinite loop, but this is not completely true. Let us run the program to see what happens. So if I run the program, there we are. It results in an exception which says exception in thread main java.lang.stack overflow error. Also notice that the function simple was called many times before the exception was thrown. However, it's not infinite. Now let us dwell deeper on what is stack overflow error and why it is occurring in this case. Earlier I said that to understand recursion, one must first understand recursion, and that was in jest. But on a more serious note, to understand recursion, one must understand stacks. One of the reasons which makes it difficult for students to understand recursion is the lack of understanding of function calls itself. And usually that understanding is oversimplified and a lot of details are left out. Now we'll dive into some of those missing details. Let me give you a brief introduction of what a stack is. A stack is a way of storing in which the items to be stored are thought of being stacked on top of each other, just like a stack of books. The important thing is that addition and removal takes place from the top only. So when we add something, it is added on top. And when we remove something, it is removed from the top. Let us understand the concept of a stack with the help of an example. Right now the stack is empty, there is nothing onto the stack. Now we'll add one element to the stack, and by the way, adding an element is also known as push. So if I add an element, it will be added onto the top. And if I add another element, it will be added on top of the previous one. And this will go on if we add more elements like 3, then let's say if I add 4 and so on. Now, when we remove an element, and by the way, removing is known as pop. Adding is known as push, removing is known as pop. So if I pop an element, that element will be popped from the top. That means first 4 will be taken out, then 3 will be taken out, then 2 will be taken out, and so on. Notice that the last thing to be added is the first thing to be removed. Due to this behavior, stacks are known as last in, first out structures. When it comes to function calls in Java, each function call creates a new stack frame. This stack frame contains the necessary information to perform the function call, such as the parameter passed to the function, the return address, and the local variables. The stack frame is pushed onto the stack when the function call is made, and it is popped from the stack when the function returns. Let us consider an example to illustrate this concept. So let's consider an example. Let's say we have a function sum which accepts two parameters a and b, computes their sum in the variable c, and returns the sum. This function is being invoked from our main method, that is from line number 4. When we'll call the function, the stack frame for the sum function will be created and pushed onto the stack. So let us visualize the code. Right now the frame contains main:3. That means we are on line number 3 of the method main. So if I press the forward button, you can see now the variable a has been created onto the current stack frame. If I press forward again, you will notice that there's a variable b also with the value 10. And now we are about to call the sum function and store the return value in the variable c. So we are at line number 4. There are two variables a and b with the values 5 and 10 respectively. Now notice this is the current stack frame, and as I told you earlier, when we push an element on a stack, the element is added on the top. So here when we are not pushing a single element, we are pushing an entire stack frame. So if I press forward again, see, a new frame has been added for the method sum. The current line number is 8 and we have passed the two variables a and b. Again, the value of a has been passed into this local variable a, and the value of b, that is 10, has been passed into this local variable b. Please note that even though the names are same, these are two different set of variables, and the computer is not going to get confused. Why? Because at any given point of time there is only one active frame. You can see this blue background over here denotes the active frame. So there are two sets of variable for a and b, but the active frame is the top frame. C is equal to a plus b. So if I click forward again, we'll see that the variable c is now equal to 15. 5 plus 10 is 15. And when I'll press forward again, this value c, that is 15, will be returned, and that will be stored in this value c. And again, even though the names are same, computer is not going to be confused, because then when we'll return, then the active stack frame will be the lower one. So let's see. So when we return, the return value is about to be 15, and see, the older thing has been removed from the top of the stack, and now we are again back to the initial frame. So that's how stack works. It's important to note that each function call creates its own stack frame, so multiple stack frames can be present on the stack at the same time. Each stack frame is separate from the others, and each has its own set of parameters, return address, and local variables. Also note that the space allotted for Java stack is limited, and even if no argument is passed, some space will be required for storing the return address and local variables, if any. Coming back to our original recursion example, the stack overflow is occurring because we are recursing repeatedly. That is, we are calling the function simple from within the function simple. Each recursive call is creating a stack frame, and since we are not returning, no stack frame is being removed, leading to all space allocated for the stack to be used up, and that results in stack overflow error. Note that the stack overflow error disrupts the normal flow of the program, and the program is aborted. Hence, it is very important to ensure that the recursion terminates, and for this there must be a base case or an exit condition to stop the recursion and return the answer. Recursion is the process of solving a large problem by reducing it to one or more sub-problems which are identical in structure to the original problem and somewhat simpler to solve. Once that original subdivision has been made, The same reducing technique is used to divide each of these subproblems into new ones which are even less complex. Eventually, the subproblems become so simple that they can be solved without further subdivision, and the complete solution is obtained by reassembling the solved components. Now let us see how we can apply the concept of recursion to solve simple problems. Our first example will be to compute the factorial of a number. So what is a factorial? A factorial of a number is the product of all positive integers less than or equal to that number. For example, 5 factorial is equal to 5 into 4 into 3 into 2 into 1, which is equal to 120. Let us now write the formula for finding the factorial of a number n. So n factorial is equal to n into n minus 1 into n minus 2 into, and we'll keep on doing this till we reach 1. So let's say into 2 into 1. Also, 1 factorial is 1 and 0 factorial is also equal to 1. So let's develop a recursive solution to find the factorial of a given number using Java. The base case is when the number is 0 or 1, that is 1 factorial is equal to 1 and 0 factorial is equal to 1. When the number is 0 and 1, the factorial is 1. If the number is greater than 1, then we can represent the factorial in terms of factorial itself, that is n factorial is equal to n into n minus 1 factorial. And we can call the function again with the argument n minus 1 until we reach the base case. Now let us see this in code. So I want to write a function to calculate the factorial of a number. The function will be public and static. Public so that it can be accessed from outside the class. Static so that we don't have to create the object. The return type will be an integer. Why? Because when you calculate the factorial of a number, the answer is integer. We'll call the function factorial. Factorial with a small f, not with a capital F. It's the convention in Java that methods begin with a small letter. So that is what we are doing. And then let's say the argument is n. Now our base case is that if n is equal to 0 or n is equal to 1, we'll say return 1. And if that is not the case, we'll say else return n into factorial of n minus 1. Now let us also have our test cases. So for that, I'll go to main and we'll say system.out.println and we'll call the function with few known values. So the first known value is 0 and the answer in this case should be 1. Let's say the second known value is 1 and the answer in this case is also 1. And let's say for the third case, I enter 5 and the answer in this case will be 120. Let us see whether this program works or not. So we'll go and we'll run the program. And if the program is correct and we are getting 1, 1 and 120. I'll be animating this program with Giliot so that we can understand it better. I've pasted the program in Giliot and we'll be animating it for the factorial of 5. Let's begin. So first main will be initialized. Now the main is initialized, the stack frame for the main is ready. Now we are calling the function for the value 5. And the first step is we'll check whether or not 5 is equal to 0 or 5 is equal to 1. Neither of the condition is true, so we'll move on to the recursive step. And here we'll do 5 into factorial of 5 minus 1, that is 4. The function will be called with the value 4. Now we'll again check whether 4 is equal to 0 or 4 is equal to 1. Both the conditions are false. We'll again move on to the recursive step. This time we'll be doing 4 into factorial of 4 minus 1, that is 3. So the factorial function will be called again with the value 3. And then again we'll check whether 3 is equal to 0 or 3 is equal to 1. Neither of the condition is true. So we'll again move on to the recursive step. we'll say 3 into factorial of 3 minus 1, that is 2. Again, the factorial will be called, and this time the value of n will be 2. Computer will again check whether 2 is equal to 0 or 2 is equal to 1. 2 is neither equal to 0 nor equal to 1, hence we'll again move on to the recursive step. And this time we'll be doing 2 into factorial of 2 minus 1, that is 1. Now I'm pausing it for some time. Now notice there are lots of stacks frame now. That means for each of the function call there is one stack frame. So there are 5 stack frames, which means that the factorial method using a recursive technique will be taking more memory. Okay, so let's continue. So now what will happen is that computer will check whether n is equal to 0 or 1. N is not equal to 0, but n is equal to 1. And hence the value of 1 will be returned. Now notice that this value of 1 will be returned to the previous call. That is, let's resume it again. Once the value 1 is returned, computer will multiply the pending expression, that is 2 into 1 is equal to 2. Then this 2 is returned, and then 3 into 2 is equal to 6. Then 6 is returned, and the next pending operation is 4 into 6 is 24. And then 24 is returned, and then finally 5 into 24 is 120. The value 120 is returned to main, which is then printed onto the screen. So this is how a recursive method works. It is important to recognize that recursiveness is a property of the solution to a problem and not an attribute of the problem itself. In many cases, we can take a problem which seems recursive in its structure and choose to employ an iterative solution. Similarly, recursive techniques can be used to solve problems for which iteration appears more suitable. There is one more thing which I would like to point out, and that is regarding the base condition. Here we are using n is equal to 0 or n is equal to 1. We have done this because this is how we usually define factorial recursively. However, in this case, n is equal to 1 is redundant. We can simply remove n is equal to 1 and the method will still work, but it will require one extra call to reach from 1 to 0, but at the same time it will save testing of 2 conditions on each invocation. The performance gain will be negligible for all practical purposes, but I think it is worth it as it makes the solution simpler. Let us move on to our next example, which is GCD or greatest common divisor. Before we dive into the code, let's understand the Euclidean algorithm for finding the greatest common divisor. The algorithm is simple and it involves repeatedly dividing the larger number by the smaller number until the remainder becomes 0. The smaller number is then the GCD. Let's start with an example first, and let's say the two numbers are 84 and 36. So we'll divide 84 by 36. 36 into 2 is equal to 72, and the remainder is 12. And since we have to repeatedly divide, so now 36 will come over here, and then we'll say that 12 into 3 is 36, the remainder is 0. When the remainder is 0, this is our base condition, and we'll stop further division, and the last divisor is the GCD. Also notice that it is not necessary to check for the bigger number. Even if we do proceed in the reverse direction, that is, if we say that 36 divided by 84, notice that 84 into 0 is 0, remainder is 36, then we'll bring down 84, and from this point onwards the solution is same as it was before. So 36 into 2 is 72, remainder is 12, 36 goes down, 12 into 3 is 36, remainder is 0, and the last divisor, that is 12, is still the GCD. So there is no need to check which one is larger, which one is smaller. We can straight away move on with the division. Now let us dive into the code. So let us code the algorithm which we just discussed. So we'll again have a method public static int. We'll call the function as GCD, and this time we'll be passing 2 arguments, int a comma int b. Now, if the divisor, that is, if the second number, in this case b, is equal to 0, we'll say return a, that is the last divisor, and otherwise we'll say else return, and we'll call the function again, but this time the first number will be the second number and the divisor will be the remainder, that is a modulus b. Let us write a test case for the same. So we'll say system.out.println, we'll call the function gcd, and we'll have the same old example which we tested, that is 84, 36. We'll also test this for 3684 for the sake of completeness. So 3684, obviously the answer should be the same, that is 12, in case our program is working, which I believe it should. So let's run the program and see what happens. So if I run the program, we are getting 12 in both the cases, and thus the program is working. Let us animate this program also to understand it better. And this time I am calling the GCD with the values 36 and 84. So let's compile and run. So first main will be initialized, and after the main is initialized, then we'll be calling the function GCD with the argument 36 and 84. So 36 and 84. Then we'll check whether or not 84 is equal to 0. It is not equal to 0. We'll again call the GCD function, but this time the divisor will be the remainder. So 84, 36 is called. Again, we'll check whether 36 is equal to 0 or not. 36 is not equal to 0. So we'll again find the remainder, and the remainder will become the second argument again. Again, we'll check whether 12 is equal to 0 or not. 12 is not 0. So we'll again find the remainder, and again we'll perform the recursive step. This time the second argument is 0. So a will be returned, that is 12 will be returned. And then this 12 will further be returned till we reach the main method. And finally, when we reach the main method, that 12 becomes the answer. Our next example is the recursive binary search. This search algorithm is one of the most efficient ways to search through large amounts of data. It's divide and conquer method that continually divides the data set in half until it finds the desired item. But there is one prerequisite, and that is the array must be sorted, either in ascending order or in descending order. For the purpose of this example, I'll assume that our array is sorted in ascending order. So let's say this is our array, and we are assuming that it is sorted in ascending order. Let's further assume that the name of the array is AR. Initially, we'll have to search in the entire range. So let's say our initial lower bound, that is the left hand side value, is lower bound, and the initial upper bound is known as upper bound. And lower bound is positioned at the 0th element, and the upper bound is positioned at the highest element, that is array dot length minus 1. The item which we will be searching for, let's say it is called item, and it is stored in a variable by the name of item. For the sake of simplicity, I am assuming that the array is of type integer, and obviously the item is also of type integer. Binary search works by dividing the array into two parts and checking the middle element. So we'll require one variable by the name of mid to point to the middle element. If the middle element is equal to the target value, then the search is complete. If the item is smaller than the middle element, then the item lies on the left hand side. If the item is more than the middle element, then the item lies on the right hand side of the array. Let's say if the item is 7 and the middle element is 25, 7 is less than 25. So in the next iteration, we'll be searching in this region. That is, upper bound will move before the middle element. But if the element, or rather the item, is more than the middle element, let's say 71, then 71 lies on the right hand side, and hence the lower bound will move after the middle for the next iteration. The process continues until either the item is found or all elements have been checked. The algorithm's efficiency comes from its ability to reduce the search space by half with each iteration. Let us see how we can implement binary search in Java using recursion. We'll start by writing a function that takes an array of integers, the item, and the lower and the upper bound of the search space. So let's begin. Public static int. I'm taking the return type as an int because I want to return the position where the element is found. So int, we'll call it recursive binary search because we are doing binary search. Let's say the name of our array is AR. We'll say that the item is item, and then we'll have the lower bound and the upper bound. Okay. Now our search will continue till the lower bound is less than upper bound. If the lower bound crosses the upper bound or the upper bound crosses the lower bound, then the element is not there. If lower bound is more than upper bound, we'll say return -1. Note that the valid positions for an array starts from 0. So if we are returning a negative value, we are trying to indicate that the element does not exist. Otherwise, we'll find the middle element. We'll say int middle is equal to lower bound plus upper bound divided by 2. And then we'll check whether or not the middle element is equal to the item. So if AR of mid is equal to item, that means we have found the element. And when we have found the element, then we'll say return the middle position, that is return mid. Otherwise, we'll check whether the element lies on the left or the element lies on the right. So if the item is less than AR of mid, the item lies on the left hand side, else the item lies on the right hand side. If the item lies on the left hand side, we'll again call the recursive binary search method. We'll say recursive binary search. The array will remain the same, the item will remain the same, the lower bound will remain the same, but upper bound will be 1 less than the middle element. So we'll say middle -1. However, if the element is found on the right hand side, we'll again call the recursive method, that is the recursive binary search. Again, the array will remain the same, the item will remain the same, the lower bound will be the element to the right of the middle, that is, we'll say middle +1, and the variable upper bound will remain the same. Now let us make the driver function for testing this method. So we'll first create an array. So we'll say int AR is equal to, now we'll have to fill the values, and the values must be in ascending order, and to keep it simple, I'll just say 1 2 3 4 5 6 7 8. So this is our array. Next we need the item to be searched. So let's say the item is, say, 6. Then we need to find out, or rather specify, the lower bound and the upper bound. So initially the lower bound will be equal to 0, and initially the upper bound will be equal to the rightmost element. So upper bound is equal to AR dot length minus 1. And then we need to search and get the result. So we'll say result, or rather let's call it position. So we'll say position is equal to recursive binary search, and then we'll pass the array, the item, the lower bound and the upper bound. Then we'll check if position is equal to -1, we'll display the message. We'll say item not found. Else we'll say item found at the given position. So we'll say item found at index position. Let's format the program, let's save it, and let's try to run it. And before we run it, let's see what should be the answer. So we are trying to search for the item 6, which is at the position 0, 1, 2, 3, 4, 5. So let's run the program and see what happens. So if I search, run the program, we are getting 5, 0, 1, 2, 3, 4, 5, which is correct. And let's say I try to search for something which is non-existent, that is 16, and I again run the program. We are getting item not found, which is also correct. Now notice that this call over here is not looking very elegant. When someone is trying to find something inside something, that is, we are trying to search for an item inside an array AR, it looks a bit odd that we also have to pass lower bound and upper bound. So we can make it look better by using overloaded method. That is, I can create one overloaded method. That means I'll create one more method which will not take those extra arguments. That is, I'll remove this over here. And then what I'll do is I'll remove this extra items from here also. So now when this call is made, this function will be called, and from within this function we'll make the actual call. That is, we'll say recursive binary search, and obviously we have to pass the lower bound, that is 0, and the upper bound, that is AR dot length minus 1, and then we can get rid of these two lines from here. So I believe that this looks better. We are performing a binary search, and for performing a binary search we need two things: where we want to search and what we want to search, and then this is the actual recursive call. Note that this is not necessary from the examination perspective, but this looks more elegant. With this, we have reached the last problem mentioned in the syllabus, which is the conversion of representation of numbers between different bases. And this also happens to be a bit more involved than the other problems mentioned in the syllabus. The problem basically means that we have to develop a recursive function, let's call it convert base, which accepts n, the number to be converted as a string. This number is in some base which we are denoting by the argument from base, and then there is a target base, that is the base to which we want n to be converted to, denoted by the argument to base. Also notice that the return type of the convert base method and the number to be converted, that is n, are both string. This is because numbers in base 11 and above will require alphabets to be used as digits, because there are only 10 digits available to us, that is 0 to 9. For example, if we want to convert n to hexadecimal, that is base 16, the result may contain the alphabets from A to F as digits. A decimal number is converted into binary by repeated division by 2. A decimal number is converted into octal by repeated division by 8. And a decimal number is converted into hexadecimal by repeated division by 16. In fact, the idea can be extended to convert a decimal number to base n by repeated division by n. To convert a binary number to decimal, we need to perform a multiplication operation on each digit of a binary number from right to left with powers of 2 starting from 0 and each result to get the decimal number of it. The same idea applies to other bases as well. However, instead of 2, we multiply by powers of 8, 16 or n. Let us understand this with the help of an example. Let's say we want to convert 26, which is in base 10, that is decimal, into binary. So what we'll do is we'll repeatedly divide 26 by 2 till we get a 0. So let's begin. So we'll have 26 and then we'll repeatedly divide by 2. 2 into 13 is 26, remainder is 0. 2 into 6 is 12, remainder is 1. 2 into 3 is 6, remainder is 0. 2 1s are 2, remainder is 1. And finally, 2 into 0 is 0, remainder is 1. And once we get a 0, we stop further division. And then what we do, we take these remainders in the reverse order. That is, 26 to the base 10 is equal to 11010. 11010 in decimal. The procedure will remain same for other bases. However, for bases above 10, the remainder may be of 2 digits and then we'll have to convert it into an alphabet. Let us see this with the help of an example. So let's say now we want to convert 26, which is in base 10, into hexadecimal, that is base 16. Now base 16 means 0 to 9 and then we'll be using A, B, C, D, E, F. So let's begin. So we'll say 26 divided by the base, that is 16. So we'll divide by 16. So 16 ones are 16, remainder is 10. 16 into 0 is 0, remainder is 1. And once we get a 0, we stop further division. But here, notice that the remainder 10 is of 2 digits and that is not allowed. So what we'll do is, we'll replace this 10 by the alphabet A. And then we'll take it in reverse order. So 26 to the base 10 is equal to 1A in base 16 or hexadecimal. If the remainder is 10, we'll replace it by A. If it is 11, we'll replace it by B. If it is 12, by C. If it is 13, by D. If it is 14, by E. If it is 15, by F. And let's say the base is more than 16. Let's say 18, that is 15, 16, 17, 18. Then there is a possibility that we might get G, H, and I as well. However, for simplicity, we'll assume that we are not dealing with bases which might result in alphabets more than Z. Let us see how we can go back to the decimal as well. So let's say we have a hexadecimal number 1A, which is in the base 16, and then we want to know what it is in decimal. So what we'll do is we'll say 1 into 16 to the power 1 plus A into 16 to the power 0. And then this will be 16 and here we'll have to say 10 instead of A and then we'll do the multiplication. So we'll get 16 plus 10 into 1 because any number raised to the power 0 is 1, and finally we'll get back 26. The procedure will remain more or less the same if we want to convert from binary to decimal. However, instead of multiplying by powers of 16 like in the case of hexadecimal, here we'll multiply by powers of 2. So this will be 1 into 2 to the power 4 plus 1 into 2 to the power 3 plus 0 into 2 to the power 2 plus 1 into 2 to the power 1 plus 0 into 2 to the power 0. So 2 2s are 4 2s are 8 2s are 16. plus 2 2s are 4 2s are 8, plus 0 into anything 0, plus 1 into 2 to the power 1 is 2, and then again 0 into anything is 0. So if we add these, 16 plus 8 plus 2 is equal to 26 in base 10. Let us see how we can translate this into code. But before that, I would like to stress on one more important point. And that important point is that when we convert the integer n from base to the target base, that is 2 base, we have to go through via the decimal root. That is, we'll first convert the number n into decimal, and then from decimal we'll convert it into the target base. We have already seen how we'll make this transformation and this transformation. Here we'll multiply by the powers of the base, and here we'll divide by the required base. This is how we'll break the problem into different methods to simplify development as well as understanding. The top level method will be convert base, which will be called by the user to convert n from the required base to the target base. This convert base method will call two other methods, both of which will be recursive, called other base to decimal and decimal to other base. The other base to decimal will cater to the first half of the problem, whereas the decimal to other base method will cater to the second half of the problem. Let's begin coding. So the first function we'll make is the other base to decimal. Public static int other base to decimal. And we have to accept two arguments over here. The first one will be the number in the string format. As discussed, it is string because in other bases, like bases higher than 10, alphabets will be used. And then we need from what base we want to convert. So from base. Now let us also make a test case so that we can test it once it's done. So system.out.println, and we'll say other base to decimal, and then we'll give some known case over here. So like in the example I checked for 26, so this is what we'll do. We'll say that we want to convert 1a, which is in base 16, and the answer should be 26 if the program is working properly. Okay, so let's begin. So what we'll be doing is we'll be taking out the last digit and then multiplying it by powers of from base, and this will be done repeatedly. That is, first a will come out, next time 1 will be passed. If it's a bigger number, let's say instead of 1a it is 1abc. First time we'll take out c, then we'll pass 1ab, then we'll take out b, then we'll pass 1a, then we'll take out a, and then we'll again pass 1. So that is the broad outline. And as far as the base condition is concerned, there will come a time when the string will become null, that is the length will be equal to 0, and then we'll return a 0. So let's start with the base case. So the base case is whenever the length of the number is equal to 0, that is our base case, and in that case we'll be returning 0. Then what we have to do is we have to take out the last digit. So let's call it last digit, int last digit is equal to, and we'll take out the last digit from n by saying char at, and then we'll give the last value, that is n dot length minus 1. So this is the last digit. Now note that the number is in string format. For example, if the number is 1a, we are extracting a, and since the last digit variable is an integer, it is actually holding 65. So we have to convert it into the actual number, that is 0 to 9. But if it is a, we want to convert it into 10. If it is b, we want to convert it into 11, and so on. And for that, we have to check whether or not the last digit is an alphabet. So if last digit is more than or equal to a, please note I'm writing a in single quotes, so actually it will be translated into 65, and last digit is less than or equal to z, that is z will be translated into 90. So if this is the case, what we'll do, we'll say that we want 10 or 11 or whatever the case may be. So we'll say last digit is equal to last digit minus, we have to subtract, because please understand, if it is a, it is 65, and if it is 65, we want to subtract 65. So I'll say minus a plus 10, because ultimately what we want is that if it is a, we want 10, if it is b, we want 11, and so on. So this is done. Now if it is not an alphabet, what we'll do is we'll just subtract 0. So we'll say last digit is equal to last digit minus 0. So just to emphasize, if the last digit is 0, that is 0 in single quotes, 0 minus this is actually 0 minus the code of 0, which will be equal to 0. So that is how we are translating a character into the actual number. So once this is done, the recursive step is quite straightforward. We'll say return last digit, this we have already extracted, plus from base, we have to multiply it by the respective powers, and then we'll say into, because we have to multiply other base to decimal, and then we just can't pass n, we have to pass the remaining portion. That is, we have already taken out the last digit, like in this case a, and we want to return the remaining portion, that is everything to the left of the last digit. That is, we'll say over here n dot substring 0 comma last but 1, that is n dot length minus 1. Now the code is not fitting onto the screen, so we'll reduce the size by 1. And there's one small mistake over here. This should be else. If it is not the capital letter, then we'll check for the small letter. If it is not the small letter, then we'll assume that it's a digit. Here our basic assumption is that the input is correct. Otherwise the program will contain more test cases to check whether or not the input is correct. Okay, let's run the program and see what happens. If the program is running, we should get the answer 26. So here we go. And we are getting 26. So our first part is done. Let's move on to the next part. We have done other base to decimal, and now we have to go from decimal to the other base. So let's begin. Public static, and this time the return type will be string, because other base can be anything, hexadecimal or maybe 20, 22, 25, whatever. So public static string, and we'll call it decimal to other base, and then we'll have to pass again two things: the decimal number, so this is an int, and the target base, that is 2 base. Let's have a test case for this as well. So we'll go up again inside the main, and we'll say system.out.println, and let's take the same case. So what we'll do is we'll say decimal to other base, and let's say I want to convert 26, and the target base is 16, and we already know the answer. If it is working, the answer should be 1a, that is we are going back. This is the reverse of what we have done earlier. We have to do repeated division, and for that we need the remainder. So we'll say take one variable for the remainder. Now in case the remainder is more than 9, we have to convert it into the corresponding symbol or other alphabet. That is, for 10 we want to go to A, for 11 we want to go to B, and so on. Just the reverse of what we were doing over here. And for that also we need one variable. So let's call that variable, let's say symbol. So we'll have one variable symbol. Now This recursion will keep on happening till the number is more than 0. So we'll say if n is more than 0, we'll go inside the if statement and then we have to find the remainder. So we'll say remainder is equal to n modulus whatever the base is. So we'll say 2 base. We'll keep on dividing it by 2 base. Now we have to check whether or not remainder is less than 10 or more than 10. So let's do it. So if remainder is less than 10, then we'll say that, okay, the symbol is equal to integer dot toString remainder. So we are converting it into the string. So this is done. But in case it is not less than 10, if it is 10, 11, 12 or above, we'll say else symbol is equal to, and we'll say a minus 10 plus remainder. This is essentially what we were doing earlier also. But here, as you can see from the error, the type is not proper. So what we'll need to do is, this is right now an integer. We need to convert it into string, but before that, we need to convert it into a character, spelling char, and then we'll simply say empty string plus this. So this will convert the whole thing into a string. So this is done. And now before we can move on to the main part, that is the recursive step, we have to do one more thing, and that is we have to divide the number. So we'll say divide it by the required base. And then we come to the recursive step, decimal to other base. And the number is n, and we are converting it to base. There's one more thing, and that is we have to reverse it also. And in order to reverse it, we'll just add symbol at the end. So every time it will be called, the symbol is added, will be added at the end. So it will reverse automatically. And there is one more problem. If you see over here, it is showing an error over here, and that is the function should return a string, and the function is not returning anything if the condition is not true. So we'll go to the end and we'll say return nothing. Let's run the program and see what happens. We all actually know what should happen. So we should get 1A if the program is working. Let's run it. And here we are getting 1A. So we have done the individual parts, that is other base to decimal and decimal to other base. Now we have to write the main method, or rather the wrapper method, which will do the actual job. So now we have to make the method convert base that will simply call these two functions, public static string convert base, and we'll pass the string, or rather the number in the string format. We'll tell the source base, that is from base. Then we'll have the target base, that is to base. Now there is a possibility that when the user is asking to convert from one base to another, the starting base might be 10 itself. So in that case, we will not call the other function because the number is already in base 10. So we'll check. If from base is already equal to 10, then we'll directly call the method decimal to other base because it is already in decimal, and let us pass the arguments. But if we go up and see the declaration, here we are accepting integer n, and here the n is string, so we have to convert it into integer. So we'll say integer dot parse int, and we'll convert n, and then we have to say to base to convert it into the target base. Now in case the from base is not 10, we'll say else return. And now we actually have to do two things. We'll call the function from within the function. So we'll say decimal to other base, and where we are saying from base, we'll say other base to decimal. and then we'll pass the relevant values, and the relevant values are n and from base. So this does the job. So if we are converting from base 10, then we'll directly call decimal to other base. Otherwise, this inner portion will first convert it to decimal, and then the outer portion will convert it to the target base. Let's make a test case for this. So we'll go up, and now we'll have the final test case. So we'll say system.out.println, and we'll directly call the convert base method, and let's pass the value. So let's say I want to convert 1a from base 16 to, let's say this time, binary. And 1a in binary was 11010. So this should be our answer if the program is working. That is 11010. 11010. So let's run the program and see what we get now. So we are getting 11010. You should consider animating this through Gilliot for better understanding. I'm not going to run this through Gilliot to save time, but it is advisable that you do run this through Gilliot in case you need to convince yourself regarding the flow of logic in this case. I have made a separate video on animating code through Gilliot, and you can find the link to that video in the description. So this brings us to the end of this video. We saw that recursion is a technique for solving problems by breaking them down into smaller, simpler subproblems. By doing this, one can write clean, efficient, and elegant code that is easy to understand. I've covered a lot of ground in this series, including the basics of recursion, the significance of base condition, and how to implement common algorithms like Factorial and GCD using recursion. One of the key takeaways from this video is that recursion can be a powerful tool, but it can also be dangerous if not used properly. Recursive algorithms can lead to stack overflow errors if they are not properly structured. So it's important to understand the limitation of recursion and how to design recursive algorithms that are efficient and safe. In conclusion, I hope that this video has given you a solid understanding of recursion and how it can be applied in computer programming. Remember, the key to success with recursion is to start with simple, well-structured examples and gradually build your skills from there. Your feedback is valuable to me. I want to make sure that my videos are clear and helpful. If you have any questions or suggestions for improvement, please don't hesitate to leave a comment or send me a message.